Right, so this is a projectile motion problem, and we have, first of all, let's define our axis, draw a diagram like this. This is the y direction positive, this is the x direction positive. Let's write that out. And we have a high diver pushing off a platform with initially a speed, so v0, which in this case is v0x because there's no vertical component, 2 meters per second. And he's launching up at a distance of 10 meters from the water surface, which is down here. Okay. So he's going to have a projectile or parabolic motion like this. So he's going to describe a parabola. And how are we going to work out the first question, which says, what is the horizontal distance? So what distance has he gone after 0.8 of a second? So to go the total distance to the water, that is r, but we're looking for the change in his position at a time of 0.8 seconds. Let's write down what we have. We have v0y equals 0 meters per second. We have v0x 2.0 meters per second, initial velocity in the x direction. We also have acceleration, and it's going to be minus 9.8 meters per second squared due to gravity downwards because of our choice of axes. So for the first question, A, so at some time t equals 0.800 seconds, what is his x position? So we can say if his initial x position was 0, then we're looking for delta x. That's what we're looking for. And it turns out because there's no horizontal acceleration, we can just use a very simple equation, which is delta x equals v0x times t, which is 2.0 times 0.800, and that comes to 1.6 meters. That's the answer for A. Quite easy because we have no acceleration. The next question's saying, you need to be a bit careful about what the question's asking for. At what vertical distance above the surface of the water is the diver just then? So at 0.8 of a second. So we need to find out what our y coordinate is. So this is different to the displacement from the original position. We're trying to find what our final y coordinate is. So we can use the equation of motion that says delta y equals v0y t plus at squared on 2. Now, delta y, remember, is just the change in the y coordinate. So we know what the original y coordinate was, and we want to find what the final y coordinate was. So we have yf minus y0 equals v0t plus at squared on 2. So we're after yf, so we're going to have to add y0 to both sides. Yf equals y0 plus v0t plus at squared on 2. Lucky this disappears because our initial y direction, I should put the y subscripts in there, guys, just in here, v0y and v0y. So yf, our final y position, is going to be y0 plus at squared on 2. We've got those values now. We can put them in. y0 was 10 meters. Now A is minus 9, so we can have a minus 9.8 times 0.800. Don't forget to square that. Divide by 2. And that comes to 6.86 meters. So that's our final position. Our displacement is going to be 10 minus that. So that's our answer. And the final part of the question is saying at what horizontal distance from the edge does the diver strike the water? So we're basically looking for the range here. So what we have to do here then is we have to find out from the last equation that we just used there, what is the time taken to have a displacement of 10 meters? So it happens when you have a 10 meter displacement. Okay, so we know that when we strike the water, our change in displacement is going to be our y final minus our y initial, which is 0 minus 10 meters. So when our y displacement is minus 10 meters, we're going to strike the water from that position. So we have y, I'll just, sorry, erase that. We have, well, what we're looking for here is the horizontal displacement, so looking for the time. Well, we have yf minus y naught equals v naught t plus at squared on 2. Okay, so this guy is going to disappear because that's the y component, and we know this value here is minus 10, so we get minus 10 equals at squared on 2, and we can just rearrange that for t now. So we get t squared equals 2 times negative 10 over a, square root that to find t, and we get an answer there which is 2 times negative 10, so square root of. Right, in this problem we have a projectile motion problem. We have a high diver pushing off horizontally with a speed of 2 meters a second from the platform edge, 10 meters above the surface of the water. Start by drawing a diagram, and with some axes. So you've got a platform sitting up here, and this is the y direction, and then you got some water down here, and this is the x direction, positive x direction. So make those definitions. We can draw some stuff on here and say that this is 10 meters, and then we've got some parabolic motion where he flies off and strikes the water after some distance, and that distance is the range r. What else do we have in the question? Well, we have that he pushed off here horizontally, so v naught is equal to v naught x, and that is 2.0 meters per second. That's the information we have. Let's write out some other things we have then. We have then that v naught y is equal to 0 meters per second. Okay, there's no velocity in the y direction. Velocity in the x direction is 2.0 meters per second. Write these things down. Acceleration in the y direction is negative 9.8 meters per second squared, and acceleration in the x direction is 0 meters per second squared. So at some time, at time t equals 0.800 seconds, we are asked to find a, the horizontal distance from the edge that the diver is after that time. So we're trying to find out in his trajectory, as he's going along this trajectory, he hits some point 0.8 of a second. Where is he horizontally? The next question asks, where is he vertically? And then we're asked to find what the range is. So let's start with question A. We've got this given time, and it's very straightforward because our movement in the horizontal direction has no acceleration. So we only have a very simple equation, delta x equals v naught x times time. That's just velocity equals distance over time. There's no acceleration in the x direction. Put some values into that. We get 2 times 0.800, and that comes to 1.6 meters. Easy. So that's the first question done. Question B is asking us to find what his vertical component, or where is he vertically in his trajectory according to this coordinate system. Well, we have to use a different equation for the position for this case. Remember, we can break up our parabolic motion into motion in the x, motion in the y. Because we have some acceleration, so we have v naught yt, but because we have some acceleration, we have to take that into account, so at squared over 2. Remember that delta y is the final position in the y direction minus the initial position in the y direction. v naught yt plus at squared over 2. We're going to have to rearrange this now. We're trying to find yf, our final y position. So what is this position here? Where is he at this point in time? So we need to get yf, so we have to rearrange our equation. Yf equals, add y naught to both sides, y naught plus v naught yt plus at squared over 2. This bit will disappear because v naught y was 0. We had no initial component of velocity in the y direction. So we get y naught plus at squared over 2. We can put some values in for this now. We started at y equals 10 at this point here. That's y equals 10. So 10. Now we've got a minus sign for our direction of gravity acceleration. So that's 9.8 times t, which was 0.8 squared, all divided by 2. So that comes to final position of 6.86 meters above the water. That's what the question's asking for. Great. Okay, so that's cleared that up. The last question, C, is asking what horizontal distance from the edge does the diver strike the water? So that's the range that we're looking for here. So that happens when delta y equals minus 10 meters. So we've undergone a displacement of minus 10. So we started at 10 meters, and then we've done a change in our displacement of minus 10 to end up with a final a position of 0 meters relative to our origin here. Right. So we can use our equation of motion, delta y equals v naught y t plus at squared on 2. Again, we get rid of this part because we've got no initial component there. So we get at squared on 2. Rearrange that for the time here because we're trying to work out the time, because the time it takes for the projectile to strike the water in the y direction is the same as the time it took to go in the x direction. So the time is the linking variable here. So let's solve for t. Using that equation, we're going to get t squared equals 2 delta y over a. I'll just scroll down a bit. So t is the square root of 2 delta y over a. We can put some values in for that now. We have 2 times negative 10 over negative 9.8. It comes out to be 1.42 seconds. That time is a time that we put into another equation of motion for the horizontal direction. So delta x then is v naught x times the time, which is 2.0, that was our initial velocity in the x direction, multiplied by 1.42, and we get an answer of 2.86 meters. That's our final answer. So we have to be a bit careful here with the signs. It's very easy to muck that up. Also, displacement and our coordinate, be very careful about that in a problem. In this question, we have a block projected up a frictionless inclined plane with initial speed of 3.5 meters per second, and it's sent up at an angle of the incline at 32 degrees. Now this is an example of when we would use Newton's second law to link the forces acting here, the net forces, to the net acceleration of the object, and then from the acceleration be able to work out how far it goes up the plane, how long does it take there. So now, it's a great example of how forces are linked to kinematics through Newton's second law. Let's draw the problem first. And we should probably define some axes. Say this y here is y is positive, and this way x is positive. Okay, so we've got our. You could do the this actually some other way, but you just have to be careful with the directions of your signs of velocity acceleration. So let's just do it this way for starters. Theta equals 32 degrees, and you've got a block here, and it's got some initial velocity like this, v0. Okay. So how far up the plane does the block go? Well, we're going to look at the forces on this object that are acting, but we'll start off with all of the forces, and then we'll look at the forces that are important to the motion in the plane. So first of all, let's draw our force diagram that has all of our forces in it. We've got our incline like this. We've got the block represented as a dot. We've got a normal force coming perpendicular to the plane, Fn, and we've got mg acting downwards. So that's the weight of the object acting downwards. Remember, we've got our axes that look like this. This is positive y, and this is positive x. Right, so we are really only interested in the forces parallel to this slope. First of all, what I'll do is I'll redraw this mg acting downwards, and you've got your slope like this. It's actually made up of a couple of components. It's got one this direction, which is perpendicular to the slope, and this is theta in here. This is mg cos theta. You've also got one that's parallel to the slope. That's the one we're interested in, the component of mg acting downwards that's acting along the slope. It's not this component here doesn't do anything to the motion. There's no component of gravity there that acts on this object at all, apart from stopping it from jumping off the plane. So the one we're really interested in is this one here, mg sine theta. That guy is the thing that's going to start accelerating the block down the plane due to gravity. That's the component of gravity that's actually going to act along the plane. So that's the one we're interested in. And that guy there, this force, is going to give us some acceleration. So therefore, mg sine theta equals mass times acceleration, and the acceleration is what we're looking for. So the masses cancel. We're frictionless here, which means that mass is going to cancel out. So we end up with the acceleration is equal to g sine theta. We can work out what that is. It's 9.8. We've got to be very careful here with the sign. We've assumed that down the plane in this direction is positive. So gravity is going to be acting positively in that direction, so we use 9.8 and not negative 9.8. And the angle is 32 degrees. So that comes out to be 5.2 meters per second squared. That's our acceleration. So we've used the force, mg sine theta, the net force. The only force acting on this thing is the gravity acting down the plane. That force has allowed us to find what the net acceleration is. So the net force gave us the net acceleration, and it's 5.2 meters per second squared. Okay, so the initial velocity in the x direction. Now, we've taken downwards as positive. We've pushed its actual velocity was up the plane, so it's going to be minus 3.50 meters per second. So once you've defined your axis, be very careful about your signs. Now, we want to find out how far up it goes. So it's going to go up, and it's going to have a final velocity in the x direction of 0 meters per second when it gets to the top of the arc. Okay? We need to find, so we've got, that's our variables we have, we need delta x. How far up does it go? And we connect that with one of our kinematic equations, our equations of motion. And the one that has all of those things, it has the acceleration, the velocity, final and initial, we're looking for delta x, is this one. It's Vf squared equals V naught squared plus 2a delta x. Okay, these are all in the x direction. That's the one we need. So we need to manipulate this to get our delta x with some algebra. So we're going to say Vfx squared minus V naught x squared equals 2a delta x. We need to divide this side by 2a, and we're going to get delta x equals Vfx squared minus V naught x squared, all divided by 2a. We've got all those values, we can put them in. Be careful of our signs here. We're going to have here we're going to have 0 minus negative 3.5, so that's going to be a positive, all over 2 times 5.2. This is the squared sign here, don't forget the squared, and squared, 0 squared is 0. And we get an answer there of negative 1.18 meters. That means that if downwards is positive, we have a displacement or a change in our position up the slope, and if we assume we started at 0, we're going to end up at a position that is 1.18 meters upslope. That's the answer. So that's the answer for A. Right. So the next question is saying, how long does it take to get there? Right. So we have some new variables now that we can use. So B, how long does it take? So we're looking for T. Write that down. We have a constant acceleration here. Okay, it's not changing. So we have constant A in the x direction, which is 5.2 meters per second squared. Therefore, the acceleration is the change in the velocity over time. So T equals delta V over A, which is Vf x minus V naught x, all divided by the acceleration. We have all of those values. We have Vfx is 0 minus negative 3.5 divided by the acceleration of 5.2, and we get 0.67 seconds. Too easy. Now question B is asking, what is its speed when it gets back to the bottom? Well, because there's no dissipative forces here, there is no friction acting, there's only the conservative force, which is gravity acting, you'd think that we should end up with the same speed when we come back up. We're going to go up the plane, get to 0, and we're going to, the same acceleration's acting on us in the, it's always acting in the same direction. We're going to end up at the same speed at the bottom. Intuitively, we can prove that. So just with a proof, we can say, let's start at the top with V naught x equals 0. And we have the acceleration of 5.2 meters per second squared. And we want to get back to where we started at with a displacement of positive 1.18 meters. We can use an equation of motion. We want to find what our final velocity is then to show that it's the same as before. The final velocity squared equals the initial velocity squared plus 2a delta x. We can put some values in there. Just get rid of that and put a square root over this. Then this guy cancels because that was 0. And we can say it's the square root of 2a delta x. Put in the numbers, and we get 2 times 5.2 times 1.18 square root 3.5 meters per second squared. Meters per second, sorry. That's our answer. So we proved it, but intuitively we kind of know that that's the case. Remember, intuitive thoughts can sometimes lead you astray with physics. Plane. So for block A, right, so this is a great example of how Newton's laws are connected to kinematics through F equals ma. We got an interacting system, two blocks, different masses, different kinetic friction coefficient, sliding down an incline. So assuming that the lighter block leads, we're asked to find the magnitude of the acceleration of the blocks and the tension in the taut string. It turns out that the acceleration and the tension are going to be equal in both cases for both blocks because they're interacting. This provides us with a way that we can get two equations for these two unknowns and to solve them. So we're going to have to use a few tricks here. We should start by defining an axis. So if we've got our incline like this of 30 degrees, we can say that this way is positive y and this way is positive x. It's going to make things easy for us. Okay, so we want to look at the force, so our net force along the plane. This is going to give us our acceleration along the plane. We need to draw a force diagram for both blocks separately to get an equation for each, and then solve those simultaneously to get A and T. So let's have a look at our first block, block A. And that is the lighter block at the bottom. Let us draw a force diagram for that, a free body diagram, 30 degrees. We have, just represent by a dot, we're going to have a normal force acting up this way, FA. We're going to have tension acting back this way, okay, because it's this is the leading block. We're also going to have a frictional force acting back this way. We'll call that little fa, okay, and then we have mg acting downwards. We'll call that weight of A. Instead of mg, it's a bit easier to write. Okay, so you can see that the FA, the little FA, and the tension are acting along the plane, but weight has a component along the plane that we have to work out. It also has a plane perpendicular to it, so I'll just draw that over here. If you've got weight acting downwards like this, then it has a component this way, which is perpendicular to the plane and cancels out FA, and that'll be WA cos theta, where theta is this angle here. It's also this angle here. There's also a component going down the plane, WA sine theta, and that's this one here. So it's that WA sine theta that's supplying a force in the plane, and WA cos theta is providing a balancing force against the normal force, so the thing doesn't accelerate off the plane. Okay, so another couple of things that we can write down. WA is mg, so the mass of A times g. So we might want to know what the mass is, so the weight of A is 3.6 newtons. So the mass of A then is 3.6 divided by 9.8 for gravity, which is 0.37 kilograms. Also, we know that mu Ka is 0.1. That's our coefficient of friction for block A. We can now work out what our frictional force is, because remember, frictional force, so we'll call it friction of A, is equal to mu Ka times the normal force of A. Now remember I said over here that the normal force of A is cancelled out by this guy here, so that's this. So they're equal in magnitude, and we can just write then that's equal to mu Ka times WA cos theta. We've got those values. We've got 0.1, we've got 3.6 times cos of the angle, and that comes out to be 0.31 newtons. That's our frictional force. So we got rid of one of our unknowns here. That we've worked that out. So that's block A. Excellent. We can rule a line under that and move on to block B. What's happening with block B? So again, we have to draw a force diagram, and it's going to look something like this. Against 30 degrees, I won't write that in again. You're going to have the normal force of B. You're going to have friction acting back this way again. Call that little FB. In this case, you've got tension acting down back towards the lower block. That's tension. And then we have WB acting downwards this way. So again, we're going to have that component, which is WB cos theta, and this component, which is WB sine theta. Too easy. So now we can do what we did up the top here, and we can say, WB is MB times G, sorry. And WB was 7.2 newtons. So the mass of B is 7.2 divided by 9.8, which equals 0.73 kilograms. Mu KB, so the coefficient of friction for B, for block B, is 0.2. So we can work out what our frictional force is. It's mu KB WB cos theta, in the same argument as before. Put some values in. 0.2 times WB, which is 7.2, times cos of 30 degrees. The frictional force comes out to be 1.25 newtons. Excellent. So we've got some information now that's going to allow us to set up some equations. But first of all, we have to start looking at the motion, because we want to find the acceleration along the plane. So we're going to have to look at the motion in that plane. So analyze, we'll just write that, analyzing motion along the plane. Well, for block A, let's just look at the horizontal, although that motion in that direction, we can draw another force diagram, a separate force diagram, which looks something like this. We're going to have tension acting back this way. We've also got our friction A acting back that way, and we have WA sine theta. Okay, that's all the forces along that direction acting downwards. So we can now come up with an equation that says, add all those guys together, and remember taking down the plane as being positive, so WA sine theta is a positive value. The tension then is going to be subtracted, and so is FA. And they're going to be equal to mass times acceleration. So mass of A times acceleration. This is an equation, one of our equations. So that's a very important equation. Now, if we look at block B, write that down, block B. Let's have a look at the motion just along the plane. Well, now the tension's going to be acting down. The friction's going to be acting backwards, so this is tension. This is friction of B. And also, we're still going to have this, now, WB sine theta acting downwards. So that's our force due to gravity. Okay, so if we add all those together, then we now have WB sine theta, positive value acting down the plane, plus T, because T is now acting down the plane as well, minus FB equals MBA. So now what we have is two equations with our unknowns A and T inside them. So we have to be able to eliminate one of these guys, T or A, to be able to solve this. So we've got two equations. I'll just write this. We have two equations, two unknowns. Eliminate T. Looks like a simple one, because if we now say equation 1 plus equation 2, we just add all these components. You know, if you just add this guy to this guy, just add up all those components, we're going to get a single equation. So we're going to end up with something that says WA sine theta plus WB sine theta minus T plus T, this is where the elimination comes in, minus FA minus FB equals MA A plus MB A. Okay, so these guys are going to cancel. Got rid of tension now, so we can solve for A. Just tidy the algebra up a little bit here, and we can get WA plus WB sine theta minus FA minus FB equals A outside of MA plus MB. Right, so I'll just write that out again in the way it was on the last slide. WA plus WB sine theta minus FB minus FA equals A outside of MA plus MB. We want to solve for A, so we just divide through by MA plus MB on that right hand side, and we end up with acceleration equals WA plus WB sine theta minus FB minus FA, all divided by MA plus MB. We can put those values in now. WA was 3.6 newtons plus 7.2 sine of 30 degrees. And FB was 1.25 and FA was 0.31, all divided by the masses, which was 0.37 plus 0.73. That comes out to be 3.5 meters per second squared. Finally, we have A. So once we have A, we can just sub back into one of our equations now. We've solved for one of our equations, for one of our unknowns, sorry. We can just sub back into one of the other equations. So if we just sub back, so sub A equals 3.5 back into 1 and rearrange for T. Well, 1 was WA sine theta minus FA minus T equals MA A. So rearrange that for T, we're going to get T equals WA sine theta minus FA minus MA A. Okay, so we've got all those values now. We can just put them in. WA was 3.6 sine theta. FA was 0.31 minus the mass of A. The mass of A was 0.37 times 3.5. The answer I get for that is 0.21 newtons. Great.